Hey everybody, I wanted to do a little bit of different video that I've normally done. I'm going to do this in 3 parts in this one video, so there's going to be 3 different sections. So what I want to talk about is give an update on my 3D printers. The other day I posted something on my Facebook and somebody asked me about, you know, how much has my printers broke down. And I was a little bit inaccurate when I said that I really haven't had any problems with anything except some connectors. So I want to dive into this a little bit deeper. First of all, Thunderbird number 1 right here, okay, and if you watch the TV show Thunderbirds, that's the reason I named this Thunderbird 1 and 2. But Thunderbird 1 is the oldest machine. Right now it has 4,752 hours on it, which is 198 days of continuous running. I ran 88,582 feet through it, which is 16.77 miles, which is 27 kilometers. Thunderbird 2 right now, right here, which is running right now, has on it 4,008 hours. It has 17 kilometers, 55,774 feet, which is 10.56 miles. So that's how much filament I run through these machines. This machine here, this machine here, which is the oldest, the things that have gone wrong with it, and I call it wear and tear. Now early on, there's a Penta probe right here, and this probe is what measures how close you are to it levels the bed basically. It tells this head where the unevenness in the bed is, okay? So that cable had chafed because, you know, this is going up and down and moving around and all that. Well, it's going back and forth and up and down. So that had chafed and it just quit working. If you look down inside there, you can see a little red light, and that red light essentially tells you that it's coming. The red light will go out as it comes in contact with the metal, or gets so close to the metal, which is in your bed. So essentially, that was the first thing that went wrong with this machine. Now that Penta Pro has never gone bad on this machine. Okay, so I kind of take that up as just maybe a manufacturing defect. The next thing is that the brains that live over here, and this is your power supply, but the brains over here has a printed circuit board, okay, your control module. There are little bitty plugs that go into it, and those plugs over time, they say will wear out just a little bit, and they lose their conductivity, and then they start to get hot, and they actually get hot enough that they'll decay or melt. So I kept making sure mine were pressed in all the time, and it still happened to me. So I think this was just me putting an enormous amount of time on my machines. The machines really weren't designed to be more industrial like I'm using them. So basically what happened was I tried to figure out a fix for that. How can I fix that? So what I did was I took the printed circuit board, and where the little pins are that the plug goes into, I soldered leads out on those and bought some really good high quality connectors. And I connected those between the power supply and the control module, and then the control module and the nozzle and the heated bed. So I got rid of those weaker connectors that's on that printed circuit board and soldered in directly to the circuit board my own wires that went to my own connectors. So that was another thing that these aren't industrial machines, but I was using them as industrial machines. So I really don't blame that on PRUSA at all. So I have had zero problem with bearings. I've had zero problems with the guides or the rails. There are right here basically what I call the threaded bushing, and that's what the lead screw runs up and down on this axis. This is actually, I don't know what it's really made out of, if it's polycarbonate or what, but those will wear out and you'll start getting slop. Okay, so I just printed my own out of PETG, and I had zero problems now. I mean, when they wear out, I just replace them. This first one wore out after about, gosh, this would have been at least 3,000 hours or 3,500 hours. This one still hasn't wore out. It's starting to get slop. But I took PETG and printed out my new ones. I did them once, an experiment with nylon. It worked, but I'm not sure why I didn't use the PETG. So, but that's my two machines right now. So what I wanted to talk about in this first part of this video was how well they have held up. Now, I will tell you about one modification I made. Was everybody knows on the new PRUSAs that you have the bed that pops off, so you can pop parts off of it. I got tempered steel and went out and bought the oh, I just forgot what you call the plastic that goes on this. I'll put it up here in the video. I just forgot what it's called. But it's a type of, you know, your stuff won't stick to it and it bends. So I did that myself. I modified my PRUSAs and put this on here. I put some high capacity magnets underneath here to hold it down, but I still use clips to keep it from sliding around. And I tell you, that has made these machines very industrial because I can just pop the parts right off. It's really, really cool. So that's what I wanted to do in this first part of the video, was talk about how well these machines have really held up. Now look, there's a lot of people out there that puts modifications out the wazoo on these machines. Mine are so stock, it's incredible, and they still work. They give me absolute perfect prints. So it's kind of a testament to the i3 Mark II. This is a Mark 2.0 and this is a 2.5. So that's it, everybody. So I'll be back in just a minute, and we're going to talk about the materials I use. Okay, everybody, we're back now. So what I wanted to talk about now is the materials that I use. And there's been a lot of controversy with people kind of coming after me sometimes, telling me I don't know what I'm doing or all of this. Look, I have 3D printed over 300 radial engine kits for people. I've printed virtually everything. Like, I made this little piece here that goes on my router so that I can hook my shop vac to it and it sucks the dust up as my router's running, and that way it doesn't get the room all messy. I made this little really cheap camera attachment that goes on one of my HD 4K cameras that I put on my motorcycle. I've printed virtually everything, but I did do some testing. So what I want to show everybody right here is some pieces that I had printed. One was ASA, this was ABS, and this was PETG. So the thing is the only reason I use ABS is two reasons. One is I have learned to print it. As you notice, I've got a box here that I don't have the front on it. This is the front right here that goes on it. And when I put this on and start printing, my internal temperature in here gets up to 140 Fahrenheit. And I can print ABS any day of the week at 140 Fahrenheit inside this box. It's absolutely beautiful. But the reason I like ABS is, A, I've learned how to print it. It's fantastic in the sun. It's fantastic in the for using an acetone vapor bath to smooth it to make it look like a mold. So I love ABS. Now someone's going to go, wait a minute, you like ABS in the sun? What about all of the bullshit out there about ASA versus ABS? So this piece of ABS has an entire summer in the sun sitting out in my backyard, and it has not degraded at all. Now, will it degrade in 10 years? Absolutely. Will the ASA degrade in 10 years? Probably not. So you need to understand how long do you need your part to last. ASA is a little bit more expensive, but my ABS has been fine. So all you little sniveling trolls out there that say, "Oh my God, you don't know what you're doing if you're printing with ASA and with ABS and you use it in the sun." You know, come on. And plus it depends on the color. If you print with white ABS and keep it in the sun, I've got stuff that I've had 2.5 years that's been on model airplanes in the sun and has had zero problems. All the hinges, all of the landing gear hard points, a lot of things I build on my massive model airplanes are made from ABS. Now, if I do want a little bit more strength and I definitely want it to handle higher temperatures in the sun, I go to PETG. So, you know, like these parts right here that are supposed to be really strong and they're going to hold high torque and could possibly get really hot in my trailer, these are PETG. Okay, so that's the biggest reason I use PETG, is when I know it's going to be exposed to a lot of heat. Okay, now PLA, you stick that in the sun and it will actually bend in front of your eyes if it's printed with black. So I don't even have fans anymore on my my print heads for printing PLA, because you know you have to cool it as it comes out. So I took the fans off. I have not printed a piece of PLA since these machines were a month old, and I won't. It's junk. For what I do, PLA is worthless. I have printed flex with these and it's worked out really, really good. I've printed ABS blended with polycarbonate. Now you got to turn the temperature up to about 295. These go up to about 300. So you're getting way up there, close to the max that the PRUSAs will get temperature-wise on the nozzle. So I've printed an absolute boatload of ABS. I've printed quite a bit of the ABS polycarbonate. I printed nylon. Got to make sure. Now that's another thing. You'll notice a lot of my stuff I don't keep very dry. My basement's pretty dry in the first place. The ABS doesn't seem to get affected much at all by moisture. Down here, once in a while I'll see a little bubbles maybe. I mean, very rarely do I do. The ASA, I never see it get affected. The Flex, I've never seen affected by moisture. The PETG, I haven't seen affected by moisture. But nylon's crazy. So you've got to keep nylon really, really dry. And if you haven't kept it dry, set your oven at like 175 degrees or Fahrenheit, or maybe even 150 if you can, and put it in there for like 4 or 5 hours to really dry it out. Now be careful you don't melt the spool that the material's on, and you shouldn't have many problems. So I'm very passionate about what works. I'm very passionate about facts. I hate speculation. I hate it when people say, well, that should work, and they've never done it. If you've followed all of my videos and have followed my builds and you've seen my success, it really pisses me off when people speculate, because if there's an audience watching, those other people might think that your speculation is fact. And the bottom line is, if you haven't done it, don't chime in. Okay, just don't add to the conversation unless you're asking a question. Don't say, I think this should work, unless you're experimenting on yourself, experimenting on something yourself. So one of my friends emailed me and says, you know, you become an expert at this. I don't like the word expert. I just like to say I've gotten some skills and I've gotten some experience. There's a lot of people that know a hell of a lot more about this than I do, but I've had some tremendous success. And when you start seeing, like, I'll give you an example. These little 3D hinges, these are hinge parts that go on one of my big model airplanes. This gets buried in the wing. These become hinge parts. These are all made out of PETG. They get screwed in. Keep in mind the way that the grain, what I call the wood grain, the layers, keep in mind the way the layers run on a 3D printed part. If you try to break it across the layers, it's much, much weaker than breaking it lengthwise with the way the plastic is melted. So always remember which way your grain runs for the strength of your component. And you should have a lot of success. When it comes to materials, you need to just keep experimenting. Okay? I can print ABS really, really well without this hot box on at all. Unless it's a big flat part that wants to curl. Okay? So that, oh, and another thing that you've got to really think about when you're playing with materials is your temperatures. On most PETGs, I'll start off with the bed at 100, and then after one layer I'll knock it down to 90. With ABS, I'll actually start at 90 and keep it at 90 because I want that ABS to stay warm and I don't want that ABS to start to cool and curl up off that bed. ABS will curl. So that's one reason if I'm doing a large flat piece of ABS in here, I close this box up, get up to 140 degrees in there, and I have zero problems. So that's the end of this section of the video. Now we're going to come back and talk a little bit about the engineering of some of the 3D parts that I do on the my designs and stuff. Okay, and now we're back for the last part of this. I did put the enclosure on the front of this to keep the noise down. I don't know how loud that was being picked up on the microphone. These parts don't necessarily need to be at 140 Fahrenheit in there to work. So what I want to do is talk about a little bit about the design and the way that I design my parts that I know will be 3D printed. Keep in mind when I'm building my large airplanes, I have a lathe for machining, normally aluminums and light metals. I mean, I've machined some steel, but I hate doing it. I have a lathe for turning stuff. I weld stuff. So I have all these other tools. This is only one of those tools. The beautiful thing about 3D printing is you can really get into some wild mechanical parts that are almost impossible to machine manually on a lathe. Now, if you had a CNC multi-axis and I won the lottery, I'd probably be using that a little bit more. But I love it. So now you got to weigh, what do you want this part to do? What do you want its structural? What do you want it to, its performance or its specification of its level of performance for the part? So you ask yourself, if I'm going to make a motor mount, let's say for a model airplane, and I have no screws running all the way through it or bolts, that's probably not very smart, because the way that the layers on 3D printed parts are, that is the weakest part, is the bond between the layers. So, but if you're going to build standoffs that you're going to run, let's say a 1024 bolt through, or a quarter 20 or something like that, then yeah, the ABS and compression is really, really good. If you're building like hinges like I do, where I figured out how to engineer where the grain runs, that's really good. I found out another thing too is like now I use a lot of filament, so I buy the big spools. Okay, and this is they make two sizes bigger than this. I use the push plastics. These guys are some of the, I don't know if that's focused. These are some of the greatest people that I've ever worked with. But when it comes to designing a part, I use Fusion 360. I will normally sketch it out on a piece of paper or sketch it out in CAD in 2D and just make sure I know what all the geometry of the part is. Then I'll draw it in Fusion 360, export it as an STL file into my slicer program. And this is where a lot of people forget about the structural importance of how you're going to slice that part. Some people think the more layers, the stronger. That's not true. So imagine that when the ABS is squirting out your nozzle, that is a liquid that cools as a solid. So the thicker your layer, the more melted plastic that made up, there's more density there. So as the layers bond, that's your weakness. But the thickness of the layer is strength. So the thicker layer you can print, even though the part might not look pretty, because you're going to see all these layer lines, the thicker the layer, the more structural strength you have in the part. Now, to get bonding between layers, you actually want to turn the temperature up as high as you can and not get all that stringiness that when your nozzle stops printing and goes to another part, you're not seeing it still being stringy, because it's so liquefied that it's creating little hairs as it goes back and forth. Now, me personally, I printed some parts where the whole thing looks like an afro of that little bitty fine hair when it's done, and I just wipe all that off. If it's ABS, I might take and put it in my acetone vapor bath, which is a fish tank. I don't recommend anybody do this, okay? But I created a fish tank with some fans in it. I put acetone in there. As you notice, I got fire extinguishers all over the place in here. I've done it for many years, have no fires, knock on wood, but I'm not recommending everybody do it. But I made my own acetone vapor bath system and it works. Sweet. So, when it comes to designing parts, you need to ask, well, first of all, do you understand engineering? Do you understand the way things work structurally? Okay, if you're going to print something, I'll use this right here. This ABS right here was printed without being in a hot box, and I don't know if you can see it, but you can see where as it shrunk, or as pieces shrunk as it came up off the bed, it pulled the layers apart. I don't know if you can see those layers. So that's the weakest part this way. So if I would have printed this out, let's say 3 feet, and then put weight on it, it would break across the layer. If I printed it, if I had a print bed big enough to print it 3 feet this way, it would be strong as, it'd be incredibly strong. I mean, if you watch some of my other videos where I've tested how strong ABS is and breaking it, it's some really strong stuff. So, when you're thinking of designing something structurally, you need to understand what is that component doing. ABS is fantastic, almost like concrete in a way. So let's think about this. When you see a big concrete pillar holding up an overpass, it is full of rebar. So the concrete is really there just to hold the steel stable, so that the steel is the workhorse component in that. Sure, concrete has a compression value, but concrete doesn't have a great twisting value. That's the reason all that rebar is in there. So think about ABS kind of a little bit like that. If you're building standoffs for a motor or whatever that's going to hold something really strong, and you've got some regular bolts running through it, then yeah, it's going to be as strong as those bolts are. But really keep in mind when you're designing your parts, you know, all of these right here are holding big high torque servos in. And I've purposely printed them and sliced them in the correct orientation, where I'm not using the layer for the strength, I'm using the extruded melted ABS or PETG as the strength. So I hope that makes sense. I want to do this quick video in 3 segments and pretty much explain my success with these 2 PRUSA machines. I've had a lot of people say, why haven't you gotten a 3rd machine? I don't really need a 3rd machine yet. I mean, I would love to have one that prints bigger parts, okay? But I just, I also don't want to build a bigger box, you know, and I'm getting ready to redesign this box for the second, the next one will be Mark III, and I'm going to use a 1-inch thick foam. It's going to be really kick-ass when it's done. So I hope you enjoy my videos. I hope they're informative. I wanted to give an update on my machines in part 1, how they've held up. In part 2, talk a little bit more about materials. And then in part 3 here, talk about the way I design my parts to use that materials. And so far, I've had really, really super good luck with my 3D printing. So, one thing I forgot to touch on. I have done a lot of ABS with carbon fiber, and I don't want to talk a lot about it, but anytime there's a material in your melted or extruded plastic that is not a continuous liquid with it, makes it weaker. Now, it will make it lighter, but the carbon fiber that is in the ABS, the ASA, and the nylon actually is weaker. Your layer bonding's weaker because there's little bitty particles in there that aren't the extruded melted material. Are they lighter? They're much lighter, but they're much weaker, except maybe in compression. I haven't tested that. So thanks for watching my videos, everybody. Have an awesome day, and I will be back. Rock on.